All right, so you can see the title there, and this is based on my recent experience trying to integrate content on ethics and impacts into a senior design course in materials, trying to provide the students insights into how technical problems, approaches, and solutions are influenced by cultural factors. And as shown here, this combines technical, ethical, and intercultural learning objectives. Now, just as much as the technical side of engineering, I want to say that engineering ethics is essentially a form of problem solving. But on the ethical side, the issues that we contend with are primarily human factors, especially human background assumptions, or in other words, conventional wisdom. Being able to see past default expectations is the first step towards active ethical thinking. And there's nothing particularly unique about engineering in this. Any human enterprise encounters dilemmas and opportunities for decision making, and these require interpretation of conventions and often show those conventions to be incomplete, insufficient, or even inaccurate. Now, the t-shirt may be an overstatement. Not all conventional wisdom is faulty, but it is always limited in its application. Conventional wisdom belongs to groups or cultures, and the degree to which we can rely on it depends on circumstance. What's expected, where, how, why, and for or by whom. In short, cultural context. Cultural context is multidimensional. And integration of ethics into technical coursework can take a lot of directions. In the case of engineering, these are some options. How are engineers expected to act? How does engineering as a discipline fit into the larger value scheme? How can engineering enable social benefit? To what extent is thinking in engineering terms itself a substantive good? In my experience, this go-to approach is to go to a case study. Expose students to a real-world or hypothetical dilemma, have them explore it, and find the best course of action, either about compliance with responsible conduct or enactment of professional responsibilities. That's limited. It can appear tangential to the course material. It can reduce to a search for the correct rule to apply, or in the worst case, the sense that anything goes. And it can create the impression that cases are universally generalizable. Thankfully, there are other points of reference we can use. One, go to the technical matter itself. In teaching a course on thermodynamics, studying energetic processes, these principles apply so broadly to natural processes that there's a temptation to consider them as a universal criterion for assessing engineering success. And the ethical question that arises here is about the limitations of that perspective. In a course on mechanical design, we teach students to do calculations on adequate structural performance, apply safety factors to overestimate loads, account for underperformance and variations. But is that kind of numerical process an ethically adequate representation of how expert knowledge really works? We can consider ethical codes that apply to the field and how they reflect cultural factors. In an interesting case here, the NSPE code was modified in 1972 to remove an injunction against competitive bidding due to antitrust considerations. Is the profession better or worse when consultants compete to provide the lowest cost solution? International codes vary in interesting ways. In Romania, engineers pledge to work in the interest of the state. New Zealand emphasizes environmental sustainability. Japanese civil engineers explicitly value traditional building materials. What can we learn from these various local priorities? On a much smaller scale, personal experience, my father's engineering career gives an array of examples ranging from New Deal rural electrification to work at a future Superfund site, DDT manufacturing, the margins of the tobacco industry, and the military. What are the various roles of engineers there? My own past experience, not quite as vivid, shows that even mundane experiences like quality control work or projects guided by military funding or prospects of technical hype about magnetic levitating trains ask us where we should focus our efforts as engineers. Institutionally, we need students to consider how predictions about the future drive intellectual agendas. The federal government latches onto a model like this, merging nano, bio, information, and cognitive technologies, and this has real effects on what problems get attention and money. Places like Virginia Tech inevitably respond to these expectations and mirror them. And fantastic progress in data manipulation, computing speed, and other remarkable new technologies can lead people to gravitate to a path that avoids problems with more incremental prospects for change, or there's no short-circuit pathway. Thomas Malthus, for one, would take issue with the basic math here. For example, future engineering designs need to address problems with serious rate and magnitude limitations. Worldwide unemployment, near 500 million people, endemic poverty in many places, limited water and thus food, and the U.S. currently using 20% of the world's energy resources with 4% of its population. We need a different kind of imagination. This value map from the World Values Survey shows how different global cultures diverge on fundamental issues, distinguishing on two axes between survival and self-expression priorities and tradition versus secular rationality. The project research has shown those dichotomies to correlate to a big bundle of different value commitments. We don't all think or feel alike, and our values change over time, reflecting developments in science and technology. Industrialization appears to move cultures away from traditionalism. An information economy has been associated with giving way to self-expression priorities over survival. And what I've been able to show is just a grab bag of possible directions to pursue. Technical skills, professional codes, individual career paths, institutional ideologies, and global values all intersect in this story to color how we establish ethical frameworks. I think it's important for students being asked to invent the future, to learn from these details, and to take it back to the beginning. Questioning conventional wisdom requires us to understand in a multidimensional way what that conventional wisdom is, how, why, and for whom. Incorporating cultural and ethical matter more fully and contextually into technical education can serve a useful role in making better engineers.